We hope you enjoyed the lunch break, and we are after enjoying this morning in two sessions which were more with the soft disciplines, and more we shared here privacy, law, policy, and topics like these. We are about to start our technical part of the day with two sessions and a coffee break in between, and we are now starting with our first, which is our third session, and we are going to have three speakers. We plan to have the questions at the end, as we've made it this morning, except the first speaker that has to leave after his session, so we'll be able to take a few questions after this session. And our first speaker here is Professor V.S. Subrahmanian, who is a returning speaker in our conference. He is now with the Dartmouth College Distinguished Professor in Cybersecurity, Technology and Society, and he's the director of the Institute for all these topics. He is an expert in big data and in cyber topics. He have published books and many papers on these areas. And Professor Subrahmanian, it's our pleasure to have you here. Please.
Can I just stand anywhere, or do I have to stand here?
You can talk from here. Okay.
All right. So thank you very much, Yaniv. Pleasure to be back to Tel Aviv and to attend this fantastic conference. So, oops. All right. All right. Let's see. All right. So this is, as always, joint work. When any professor speaks, it's usually somebody else who did most of the work. So if you like the talk, my students and collaborators should probably get most of the credit. Okay. So what I'm going to be talking about today is work on Android banking Trojans. So you're all aware that Android is probably the most widely used operating system today. And I'm going to break my talk into 5 parts. I sent a video this morning, but it didn't quite make it, and I didn't think that I should come to a cybersecurity conference with one of these and plug it in. So if you'd like a video, let me know, and I'll put it on a share site and send it to you. But it was a video showing a particular Android banking Trojan called Marcher, which is widely used and by malicious actors. And so what I'm going to do is to talk about some of the technology we've developed to take a binary, a piece of code, and predict whether it is a banking Trojan or not. All right? So we're going to basically talk about something called a triadic suspicion graph, which consists of a new class of features that we believe are useful, that we've shown are useful. We've also shown already that our algorithm has been able to detect malware, Android malware, that was not previously identified by any of the 63 antivirus products on VirusTotal. Okay? So there are more of those coming as we speak, but it is capable not just of working on the kinds of training data that we all use, but also in the wild. So, okay, sorry, video not there. This is what a suspicion graph looks like. It's called triadic because there are 3 types of nodes. So think of a training set with a bunch of malware shown in red, which are banking Trojans down here. Goodware, pieces of code that are known to be good, and API function calls. So in this example, very small graph with just 3 banking Trojans, 3 pieces of goodware, and half a dozen API calls here. There's an edge from a piece of goodware or a piece of a banking Trojan to an API call if that code makes that call. There's an edge from an API call to another API call if that API call calls the other one. Okay? So very simple. And from this, we can define edge weights in many ways. So in this paper, we define actually dozens of different ways of defining the weights of edges. By the way, this is not a paper that's published or even submitted. It's only about half written at this point, but the research is pretty much done, and we're just writing it up. So we defined a number of ways of defining edge weights, and some examples are simply a 0-1 edge. If the call is there, it's a 1. If not, it's a 0, which means you don't need the edge. We may normalize the number of API calls in the code. We may define a monotonic function, which is monotonic in the number of such calls. We gathered actually a data set from VirusTotal of recent banking Trojans, primarily 2016 and 2017 samples. And we actually got somewhere on the order of, I think, approximately 5,000 samples of 3 categories: goodware, banking Trojans, and other kinds of malware other than banking Trojans. You'll notice that these numbers are not quite 5,000. And the reason for that is because, for those of you who do machine learning, it turns out that the way we define features, many different samples, that is different hashes on VirusTotal, ended up with the same feature vectors, okay? So that means that if you do cross-validation, you're going to artificially boost your numbers, okay? We've not really seen this discussed in the literature in any of the papers we read, but we didn't think it was right to artificially boost numbers by having feature vectors that are identical for 2 different samples, one in the training and one in the validation set. So that's bogus. We didn't want to do that. This is what a visualization of our triadic suspicion graph looks like. The blues, as expected, are goodware. The reds are banking Trojans. And these green dots that you see in the middle are a total of about 170 API calls. OK, so I'm not going to make you read the slide. But these are many possible ways in which you can define what the suspicion score of a particular API call is. And I'm not going to, as I said, there are many different ways. And I'm going to just go through the simplest way for a moment. So this says, if I look at this graph, the suspicion score of a call C is obtained by looking at basically the sum, the total. So I of BIC is set to 0 or 1, depending on whether banking Trojan I makes calls C or not. Okay? So this basically is simply the total number of banking Trojans that make the call to C divided by n, which is the number of banking Trojans. And this is the same thing in the denominator, and this is the same thing, but applied to goodware instead. Very simple. So the idea simply is that this ratio is going to be high if it's mostly banking Trojans that make the call as compared to goodware. So it's guilt by association. Very, very simple, very, very naive. I just want to point out that we have another dozen of these things which define this in different ways. And as a lot of the work we're doing is applying machine learning to do this efficiently, what we are trying to do is to do extensive hyperparameter testing to figure out which of these definitions works best. So if you look in this particular case, and we look at banking sample 1, B1, it makes calls only to this API, API 5, API 6, and API 4. And these edges are weighted with the number of calls made. And that's also one of the parameters I mentioned earlier. Now, this definition, I won't go through the full details because I don't have too much time, but if I apply this definition, what I end up with is something that looks like this. It says, look, according to this particular definition of suspicion of a call, this API call 5 has a suspicion score of 1. API call 6 has a suspicion score of 1. API call 4 has a suspicion score of 0.5. For this one banking Trojan B1, okay? So these are features associated with B1 subject to the suspicion with respect to B1. We also, extend the notion of page rank to a suspicion rank. So the definition I just gave looks at edges directly from the banking Trojan to the calls, but does not look at the intra-call relationships. So we defined a notion of scoring that takes the suspicion score of a piece of code, C prime, an API called C prime, and tries to propagate how important it is from a suspicion perspective. So for those of you who remember PageRank, do people know PageRank? Or at least you've heard of it. Okay, so very simple. What you're saying here is that this is some a priori probability of C being suspicious. That's what the first term here does. And then it says that if there's an edge from C prime to C, so a call C prime, like this one here, API 1, makes a call to API 4, this call, the call of C prime, if it's suspicious, could also lead to suspicion for this. Okay? And what this says is, I'm going to take the suspicion rank of C prime, and I'm going to look at the suspicion score of C prime, and I'm going to divide SR of C prime by out C prime, so how suspicious this is divided by the number of other calls that it makes. So if I call, if a piece of code C calls 100 possible other calls, this number would be diminished by a factor of 100. If it calls 10, it's going to be diminished by a factor of 10. Okay? So suspicion is going to be passed on proportionately by virtue of calls. So, okay, sorry. I've been talking all day, so my throat is... So if I look at this picture here, and I apply the definition of suspicion, the one definition, even though I have many more, I end up with a situation where the suspicion rank of API calls 4, 5, 6, etc. are in this order. So again, these are associated with banking Trojan 1. Then what we do is to say, well, we know in writing these features that we are wrong. Okay? I know this for sure. We're not going to be right. So how do we sort of mitigate the effects of knowing in advance that what we've got is far from perfect? So one way we did this was to say we're going to take all the suspicion ranks that we have for all the different API calls, and I'm going to order the calls in descending order of rank. Sorry, yeah. And then what I'm going to do is I'm going to use a window which says, look, these 5 calls are all in the top batch of, let's say, W is 5. So I'm going to list all the calls in descending order of rank, and then I'm going to say, you know, I don't know which of these is the most suspicious because I know that my scoring is probably wrong, so I'm going to just lump them together. So W is also a parameter that we try to identify through our cross-validation hyperparameter training. So I take these W calls and say, okay, I'm now going to lump these together and say, you know, these W calls are probably all competing for the top spot. Okay? I don't know which is exactly the top, so I don't want to say this guy is the top or this guy is the top, but they're all up there somewhere. Okay? So that's the basic idea. And then what we're going to do is I'm going to aggregate the features of these W calls to induce features for this particular sample. So again, I'm looking at sample B1. And what I'm saying is, look, I've got, suppose I take W equal to 3, then that means that these 3, by the way, this list of API calls is enumerated in descending order. So what this says is that these 3, you know, these are probably the 3 top ones. These are the next 3. And so I'm going to aggregate the properties of these. So I might say, okay, you know, is one of these called or not? And that may be a binary variable, and I set that to 1 because, in fact, in this example, each of these 3 is called. But when I do the same thing with the next batch of 3, they would be set to 0 because none of these is ever called by B1, because those are API 1, 2, and 3. Likewise, I could look and say, you know, what is the weight of the edges that are involved in these calls? So, the number of these APIs that are called. So all 3 are called in this case. So this would be 3. In this case, it would still be 0. Likewise, I could define a bunch of other aggregation functions that combine these ranks together. Again, you know, don't worry too much about the specifics. Basic idea is we're defining suspicion scores by analyzing this new type of graph. We're analyzing we're developing a version of PageRank that builds on top of these suspicion scores to assign a suspicion rank to each node. And because we know that our ranking system is imperfect, we're going to try and lump some of these things together into groups and then derive features from those. So basically what we end up with at this point in time is that for B1, we're going to get a bunch of features such as these that are associated with these groups. Okay? After this, what I'm going to do is standard predictive modeling. I'm going to do two things. One is I'm going to look at the predictive accuracy of a whole ensemble of algorithms for classification using trying to separate goodware from banking Trojans and separate banking Trojans from other kinds of malware. Again, the point I'm talking about is that our samples are non-isomorphic. So what that means is that in our data, we do not allow two samples which have the same hash. I'm sorry, which have different hashes, but which have the same feature vectors, okay? And this is, so if two samples have exactly the same feature vectors, they're very likely the same because we have in our data, I think, close to 4,000 features, okay? So if I go back here, I think when I use W equal to 5, we have almost 4,000 features in all by aggregating different combinations of these things. Oops. All right. So, okay. In addition to the features defined using the triadic suspicion graphs, we also use traditional features that have been used in the literature, okay? What are examples of some of these features? They're features based on static analysis of call graph frequencies. There are features based on manifest information, including some features I don't like a lot, like file size, number of activities, etc. We put them in there because they've been used in the literature, and we want to be able to compare against them. Now, I'm just highlighting the rows based on the suspicious graphs alone, but you can also see that there are rows here that look at the accuracies. So the accuracies we're doing are in terms of AUCs, area under a ROC curve, but I'll also show false positive results. So the good news is that we are able to get accuracies in the high 90s, okay? That's the good news. And this is on cross-validation after hyperparameter optimization on the training data alone, okay? Which is what you would expect. This slide compares goodware versus Android banking Trojans, separating goodware from Android banking Trojans. The numbers drop a little bit, again around mid-90s, but not high 90s, when we try to separate banking Trojans from other types of malware. The reason, as many of you know, is that oftentimes, for example, you may have a piece of spyware that is used as an initial attack vector to execute a banking Trojan afterwards, okay? So as an example, I mean, if you look at certain samples, Marcher is a good example, you might find that it's first acting as spyware, collecting information, and then executing malicious banking operations. So in cases like that, it's not really 100% clear whether this should be considered spyware, whether this should be considered a banking Trojan, or some hybrid of the two. So our numbers drop a little bit, still in the high 90s. And if I show you, again, goodware versus Android banking Trojans, our false positive rates are basically under 1%. Okay? So we're doing pretty well. But one reason, of course, is that we have defined a very, very large number of features, done very careful hyperparameter optimization, and done extensive training. And this is other malware versus Android banking Trojans, and again, it's less than 1%. Sorry, I take that back. It's more like a few percentage points, okay, depending on exactly which combination of features you look at. So let me say a little bit about key characteristics of Android banking Trojans versus goodware. So this is, I'm sure you cannot read the slide, okay? But the point I want to make is that these are the 25, I think, most important features. And even though you cannot read the slide, you can see that this big red bar here is very far from the blue bars, okay? So the blue bars are the goodware. The red bars show the banking Trojans. The x-axis is the value of a feature. So each of these graphs corresponds to one feature. I'll show you two of these in a minute in more detail, but each of these graphs corresponds to a feature. This is the most important feature, the second most, etc. None of these features by themselves is useful in making the prediction, okay? They're useful only in combination with everything else. So don't take away any incorrect message that somehow this feature alone can be used for prediction. It'll do a terrible job, okay, by itself. And those of you who are experts in machine learning know that this is a very common occurrence. That, if one feature explains anything, either you're very lucky or it's too good to be true. Okay? But this shows you some distributions. It says, look, there's a big blue bar here, there's a big red bar here, and they seem to be separated by lots of white space. So that suggests that when a new sample comes in and it has a feature value that's somewhere towards this end of the spectrum, it's more likely to be malware, a banking Trojan, than goodware. But doesn't mean you should use that to predict, as you may end up with a high false positive rate if you do that. Okay, let me just go over two of these in a little more detail. So this is the same picture blown up a little bit, and this is looking at receive SMS as a signal. Okay, so this is looking at permission data, looking at receiving SMSs, and we all know that why exactly should an app read your SMSs or receive them? It's something that you want to look at closely. And this says, look, this is when the feature value for this is 1, you are more likely to be a banking Trojan. If it's 0, you're more likely to be goodware. But in both cases, there are errors. There's a little red bar here, a little blue bar here. This looks at calls towards certain API calls, namely a call that displays certain UI functionality. And here again, you can see that when this feature value is sort of in this zone here, it's much more likely to be goodware. If it's close to here, it's much more likely to be a banking Trojan. But in fact, you can see that this blue bar right here is actually pretty big. Okay? So it looks small, the red dominates, but in fact, you don't want to use this to predict on its own. Again, we've got a detailed sort of understanding of the different types of features that seem to be linked. So if I did a statistical analysis, all these would turn out to be statistically significant, but they're useless for prediction on their own. They are useful for prediction in conjunction with other things. On their own, not very useful. We also did some robustness testing. So because we were downloading samples from VirusTotal, we know that anybody else can download samples from VirusTotal as well. So what if an adversary tried to recreate our training and see how well he or she could predict what we're trying to do, assuming they have exactly the same 3,960 features in the W equal to 5 case, okay? What might they do? So we said, well, suppose I have a training set phi1, which is the true training set we use, and phi2 is the training set used by the adversary, okay? What I want to do is to see how well he can do as I regulate and vary the overlap between phi1 and phi2, okay? So if this overlap is 0, then he's using a completely different training set than I am, and I would hope that I get good results. On the other hand, if the overlap is 1, then he's using exactly the same thing as I am, and you would expect him to do a lot better, okay? Especially if he knows all the features I'm using as well. So we tested this hypothesis by looking at the generated feature vectors and looking at different measures that compare the feature vectors together between the predictions we make and the predictions that are made by the adversary as I vary delta, that is the degree of overlap from 0 to 1. What you see here is probably, I think, the most interesting result. This is using a Kolmogorov-Smirnov test, but we also did this with more standard distance metrics in high-dimensional vector spaces as well. So whether I do it with different distance metrics, such as Euclidean distance, Manhattan distance, various kinds of other distance functions, we get similar results. So with the suspicion-based features, which I'm abbreviating SUS, the distance between what we are able to come up with and what the adversary would be able to come up with his training data is much higher than with any of the other measures and other classes of features that we've looked at. So what this tells us is that, and as you can see, of course, at about 80% over here and over here, that starts dropping. Obviously, the distance is going to go to 0 if the adversary is using exactly the same feature vector I am. Okay? But as long as he cannot guess more than, so basically what that means is I don't want to train with all the data that I have accessible to me on VirusTotal. I need to randomly sample this in some way so that the chance that the adversary can sample more than 80% is somewhat low. Okay? A couple of other things, and this sort of goes to some of the comments that people have asked me about in the past. So we shipped sometime, I think, in March, just to test some of our results of predictions on Android samples that were not classified as either clean or malicious by any of the 63 antivirus engines running on VirusTotal. So for those of you who are cybersecurity researchers, you know that VirusTotal is a property owned by Google. It contains a very, very extensive set of hashes. There are many, many cybersecurity companies that contribute to VirusTotal, and though it's not everybody. And so what we did was we reported 2 samples that were not known to be banking Trojans at the time to any of the, actually in one case, I think one sample, from the time we got it to analyze to the time we reported it to Google, somebody flagged it already. But in the other case, nobody flagged it. And even today, 30 commercial AVs think one of the 2 samples we looked at is clean, okay? That was not today. This was a couple of days back, okay? Before I flew in from the US, I sort of just quickly went to Google, to VirusTotal, check what happened with these hashes, and this is what I saw. So that number may have changed by today. But at that time, 30 commercial AVs took one of them, the one we had discovered before anyone else, and said, hey, these are clean, all right? So that's wrong, because we know Google looked at it and came back to us and said, these are malicious. And likewise, 31 commercial AVs did the same with the other sample we looked at. So again, I'm not an antivirus engine. I don't have the resources of a Symantec or a Checkpoint to do this on a daily basis with every malware that shows up or every potential binary that's submitted to VirusTotal. We are simply too small and poor for that. But it shows that it can actually discover things that other people have not discovered previously. So I think that's pretty much all I have to say. I hope I'm on time, Yaniv. And thank you very much. And if you want to see a video, let me know. I'm happy to show it to you.
I think that first thank you, and it's my pleasure. And I had the pleasure to visit Professor Subrahmanian's lab and to see the enthusiasm of his team to work with him on these things. So it's really exciting. And since you have to leave, so we can take a question or two before continue. So please.
What I mentioned is solving this problem because for a lot is not efficient in high dimension.
Sorry, what is it?
In what dimension the problem is?
So what we did was we did hyperparameter optimization with W, okay? So it's still in the order of thousands of dimensions. I think it was W equal to 20 that was our best parameter for W. And I don't remember how many features exactly. I just put up W equal to 5, the number of features involved. It was still in the order of upwards of 1,000 features, but I don't remember exactly.
Kolmogorov is not efficient in 1,000 dimensions.
The point is not whether Kolmogorov is efficient or not. It's just the relative positioning compared to other classes of features.
Also, there is another way to spell this problem in more elegant way.
Okay, yeah, absolutely. Love any comments. We haven't written the paper yet, so it's partly written, so I'd love any comments at this stage, yeah.
Rewrite it.
Okay, all right, fair enough.
Another question? Yeah, please.
So if I was a malicious attacker reading your paper to be published, then I would probably load my malware with a lot of redundant API calls, probably random API calls, which would, in the long run, would break your training model. So how would you do that?
So we've looked at a number of classes of attacks on the system. So one was we looked at a bunch of attacks based on various kinds of obfuscation strategies. So we're able to do pretty well against some of them, but not against all of them. And one reason, as you know, is that any method that involves any kind of static analysis can fall short. Okay. That said, you can still do pretty well with dynamic. Where is it? With combinations of dynamic features alone. Okay. So basically, again, what we are not recommending is to use SUS by itself, but some combination of SUS with other features. Okay. So you mitigate some of the risks. Yeah.
Great.
All right.
Thank you very
Thank you.
much.
Can I see another bottle?